So Llama 4 is finally out. We've been waiting for this version for quite some time, and now that it's here, it's receiving slightly mixed reactions. So I thought I would give you a short breakdown of the new models and share some thoughts on the new herd of llamas. Alright, so Meta presented 3 new models: Scout, Maverick and Behemoth. The first 2 are already publicly available and you can download the model weights on llama.com or Hugging Face. Behemoth should be available later this month. All 3 models are huge. Mark Zuckerberg said that Scout is by far the highest performing small model in its class, but I really struggled to see 109 billion parameters as a small model. The model card says that Scout can run on a single GPU, but they don't mean consumer-grade GPUs, they mean H100s, which have 80GB of VRAM and a price tag of over $20,000. I mean, it is understandable why they are making the models large. As I explained in my previous video about GPT 4.5 and scaling laws, if you want better performance, research suggests scaling 3 components in tandem: compute, training data, and model size. And they increased all 3. I just wish they had also given us a smaller, maybe less powerful model, but one that could at least run on more affordable GPUs. I'm sure many people will be fine with this, especially since it's possible to run it on multiple cheaper GPUs or even on a Mac with enough unified memory. But in my case, for example, I don't really have access to those kinds of resources for my PhD research either. And since fine-tuning demands even more VRAM, I'll likely stick with models like Llama 3 8 billion for now. So Scout is not small, but it is the smallest in the Llama herd. Maverick has 400 billion parameters and Behemoth has 2 trillion parameters. It's 20 times larger than Scout. More about it later. You can also see that each model presents the number of active parameters and the number of experts. That means one thing: Llama 4 is adopting the mixture of experts architecture from DeepSeek. I would say that was kind of expected, but the timeline is interesting. Llama 4 has been in development probably since last summer, and the latest DeepSeek models came out in December and January. So my personal bet is that they scrapped everything a few months ago and started all over using the ideas from DeepSeek. And if that's true, that's actually quite impressive, how fast they managed to implement this new architecture and train everything. I've already explained mixture of experts or MO in my previous video on DeepSeek, so I'll just give you a very short overview here. Basically, instead of the usual attention block, where the input is processed by one dense layer, Mo splits this dense layer into several smaller networks called experts. The assumption is that each expert is better at processing different types of inputs, and so when the model is about to process a token, there is a small router model that first decides where the token should go, and only those experts are activated. And there is also a shared expert that is always active. So that's what the number of active parameters means. For example, in Scout, all these experts across all layers have 109 billion parameters in total, but at any given time, it's activating and using only 17 billion parameters. A small caveat here: compared to DeepSeek, which uses Mo in every layer, Llama 4 actually alternates between dense layers and Mo. So half of the time it will use dense layers as before. The main advantage of Mo is speed, because it requires much less computation for each token. That leads to a speed up for both training and inference. And we can clearly see this speed up when we look at the training times. Llama 3 70 billion model took 7 million GPU hours to train, whereas Llama 4 Scout, despite having over 50% more parameters, took only 5 million GPU hours. So that's a clear advantage of Mo when it comes to training. And if you can fit the models in memory, both should, in theory, run as fast as standard 17 billion parameter models. Besides faster training and inference, there is another very impressive improvement here: the new context length. Previously, Llama 3 models could process up to 128,000 tokens. Now, Maverick can handle up to 1 million and Scout can go up to 10 million tokens. That's pretty insane. To illustrate the size, the book Moby Dick has about 650 pages, which is over 200,000 words or about 280,000 tokens using the Llama tokenizer. That means you can fit about 35 books of that size into the context window. However, here it's important to say that the models were not actually trained with 10 million tokens in the context. They were pre-trained and post-trained with a 256,000 context length, and Meta implemented some clever tricks to improve the generalization beyond this limit. For example, they didn't use positional embeddings in some of the layers. This decision is based on this paper, which shows that not using positional embeddings, referred to as NOPE, can actually improve length generalization. And if we look at the Llama 4 attention code, this line tells us that rope is indeed skipped every 4 layers, and the remaining 3 layers use something called chunked attention, which limits how much context each layer can see. That makes it much more memory efficient and perhaps even encourages the model to use the NOPE layers. So again, 3 out of every 4 layers operate with limited context, while every 4th layer has full access but without positional information. This apparently helps to generalize from 256,000 tokens to 10 million tokens, and they demonstrate the effectiveness of this method in a benchmark called Needle in the Haystack. This task involves using a very long input context and inserting specific information somewhere within it, like the magic number here in this example. The model is then asked to retrieve that specific piece of information. And you can see that Scout retrieved the needle every single time across different setups, all the way up to 10 million tokens. Meanwhile, Maverick did slightly worse, but both charts basically show that context length is not a major limitation here. That being said, this benchmark mainly checks whether the information doesn't get forgotten or overwritten by some other context, kind of like the issues we had with LSTMs in the past. However, from my personal experience, the performance on more complex tasks often drops with most models as we increase the context length. So I still recommend double checking the performance if you plan to use very large inputs. The other benchmark, MTOP, is probably more informative. It stands for Machine Translation from One Book, and it's a benchmark for learning to translate between English and Kalamang, a language with less than 200 speakers and therefore virtually no presence on the internet. And so in this benchmark, we basically hope that the model has never seen the language before. We give it all available resources for learning Kalamang in the context, which is, I believe, about 250,000 tokens, and then we ask the model to translate a sentence. Here you can see that humans scored a 51.6 character engram F-score when translating from Kalamang to English, and 57 when translating from English to Kalamang. Looking at Llama4 results, Scout scores around 40 and 36, while Maverick scores about 51 and 47. So Maverick is doing much better at reasoning with long contexts, but is still below human performance on this task. Now, besides the long context, we can also see several other benchmarks for image reasoning and understanding. That's because Llama4 is now natively multimodal, supporting text, images, and video. Previously, Llama3 was first trained as a text-only model, and then later in 3.2, a separately trained vision adapter was introduced consisting of cross-attention layers that incorporate image encoder representations into the language model. This setup, where each modality is trained and processed independently and then combined afterward, is called late fusion. Llama4 uses an early fusion architecture, where text and vision tokens are combined at the input level from the start. And this joint training usually performs much better. And the results look good. Personally, I'm interested in the visual QA datasets like Chart QA, Plot QA, and Dog VQA, and there you can see a solid improvement over Llama 3.2. Another interesting benchmark is the chatbot arena. There, Maverick ranks second, which is a very respectable result. I just don't understand why it's tagged as experimental here. Is this some other model we don't have access to? Why isn't it just Maverick? Anyway, the 2 trillion Behemoth model is still being trained and will likely surpass Maverick, so that will be interesting to see. And speaking of Behemoth, while we don't have access to the model yet, Meta shared some interesting details here. First, Behemoth was used as a teacher model for Scout and Maverick, and it seems they used code distillation. Unlike traditional knowledge distillation, which involves training a teacher model in one phase and then training a student model from the teacher outputs in the second phase, code distillation is a process where the models are learning from each other at the same time. And Meta developed a novel loss function that dynamically weights the soft and hard targets through training. If you want to learn more about code distillation, I think this paper is a good starting point, and I'll link it in the description below the video. The second thing we know about Behemoth is that it was trained with 32,000 GPUs and FP8 precision. That essentially follows the training setup of DeepSeek, which you can see here. I've already discussed FP8 in my previous video on DeepSeek, including how they used a clever mixed precision setup. Basically, some operations were done in FP8, while more important computations were performed in higher precision. And hopefully, if Meta releases a paper at some point, it will also include details about their training framework. That would be great to see. So overall, this release is great. I think many people will benefit from it, and I'm always happy to see any new open weight models. Compared to DeepSeek, Scout is actually a somewhat manageable size. So maybe if I manage to run it, I can take advantage of the 10 million context window for retrieval, or take advantage of the visual capabilities that DeepSeek doesn't even have at the moment. Still, I'm hoping for some smaller models in the future. There are also other things to look forward to. We're promised to get a reasoning model soon, and of course the Behemoth model. So maybe they will be released at the LlamaCon Developer Conference on April 29th. So that's all for today. Please consider subscribing if you liked the video, and thank you for watching.